Are you ready? No, I'm not. Never ready. Yes, let's go. All right. Thanks, Pablo, and the team for organizing this event and inviting me here to talk today. And also thank you to the audience, voluntarily or involuntarily, to be here and listen to me talking about physics, or maybe pizza, depends on what you're here for. All right, thanks. So hi, my name is Alan. I'm a machine learning engineer by trade, working with various startups and dev shop, and now having my own AI consultant agency, which means half of the time I spend AI to people, and the other half extend people to AI. Well, I mean, that's how it works. But yeah, quick questions. Who here did physics in high school? Oh, who here remember any of it? Okay, so yeah, I think you guys will be here instead of me. And yeah, please shout out if I do say something stupid. Backstage, not in here. Okay, so yeah, you can put your hands down. All right. Yeah, so let's talk AI. Shit. For those who are not familiar, I mean, I think all of you are familiar, but just precaution. AI is a pattern recognition machine on steroid. Basically, you show it 1,000 pictures of cats, and it pick out like if it's pointy ears or this have the thing on here. It say, oh, hey, that's a cat, but it doesn't know what a cat is. It just recognizes the pattern. And now a physics-informed neural network, I will call it a PIN, P-I-N-N, for now PIN, never mind. Yeah, PIN, it's showing the same neural network, but put in the physics class. And now it not only know what the cat is, it will also know that the cat should not teleport or suddenly gain 50 kilograms by walking. So, right. Wait, sit. There you go. Right. So, right. If you're dealing with AI before, you know that AI likes data. It eats a lot of data, mountains of data. We're talking about gigabyte, terabyte, even petabyte. Here's the data set from Hugging Face. You see, near 4 terabytes just for documents to train an LLM. And for most real-life problems, we don't have that kind of data laying out. Okay. I can hear Alan. Yeah. But yeah, so for most problems we're facing, we don't have that kind of data. I mean, you don't know how many times your dog poo-poo every day, or we don't have data laying around for rocket trajectory or microplastic in the air, so on and so forth. And sometimes there's a situation where there's a term called you have nothing, like zero, none data at all at your disposal. And so it's a catch. Like I should practice better. We know for the wait, what's that? Shit. Yeah, I know. I should have, but it's looking weird, like doing. All right. That's not cool. Yeah. So the world we're living in, we already know a lot about it. We have gravity, we have heat, we have electricity. You know, the Newton and Einstein, those kind of dead guy, already solved it already. And so there should be a way we capitalize it here in AI. And so when you train a neural network, it only sees the data you give to it. Whether it makes sense or not, it will believe it. So it can happily vaporize the entire ocean if you say it to. Even yeah, even when you have to tell it like, hey, water does not vanish suddenly. So imagine I'm a neural network, and if I pour water here, it can say both have water or both doesn't have water, but the water should be the same, right? Because conservation. And so you have to tell it the physics for it to work. Same amount of water, unless I drink it. All right. And yes, oh shit. So like a physics-informed neural network is exactly like a neural network, but there are some better stuff with that because it's based on physics, so it needs less data. Because for normal neural network, when you train it, you give it some input, it gives back some prediction, and then you compare the prediction with the desired output. And then you say, hey, you suck, get better, and repeat. But for pins, you not only compare the prediction with the output, you also plug the prediction into a physics formula, and then check if that makes sense or not. Because the cat can get 50 kilograms more overnight. And the second one is that can handle very complex problems, especially with things like atmospheric modeling and those kind of things. There are some cons for that though, because it's based on physics, and there are two sources of losses. It needs a lot more time and effort to set up correctly and train. And you have to be physics informed, because how can you teach without knowing it? So let's go to an example the only example I have. Never mind. So microplastic is everywhere now. It's in the ocean. It's on the floor. It's even in the air. You have now, and you're breathing it right now. So there are not much data around it because you can't really capture it. It's too small to find in the air, and so there's only a few studies conducted around it to measure the amount of microplastic in the air. And we want to model the microplastic concentration of the whole world. So we have to use machine learning for that because we only have a few points of data here and there. And so a group of scientists in, never mind that. Group of scientists, what? Someone say anything? All right. So a group of scientists in Germany do a study around this. They run a supercomputer in their university for over 2 weeks and get 24 images of something like this. And they got a result. They published it. I steal it with permission. And I emailed them, right? Yeah, and then, what? Did they respond? Yeah, they did. I ghosted them though, sorry. Please don't mind. Yeah, and then I used that to train my own pins. And the result is quite interesting. They have their own supercomputer. As you can see, they have like 4,000 GPU core. They have total RAM, terabyte, not gigabyte, and it runs for over 2 weeks. And then I used their result and run it on my virtual machine. It's only 6 GPU. I cheated by using a GPU. Don't tell them. Around 60 gigabyte RAM, and it trained for 2 hours. And then the process that they run in 2 weeks can now be run in 1 minute to get an image like this. Yeah, this is my result. It's quite subpar, but it's about 80% quality with 0.1% of resources used, and tiny amount of time compared to what I have. And you don't really have supercomputer at your disposal. All right. So now, if you are crazy enough to actually want to build it yourself, I have some good news for you. Just take an example. You want to know how much force this pen will hit the ground. You have the if you know the physics, it's force equal mass by acceleration. Now you know the mass. Well, you don't. I know. Yeah, and the acceleration is just the gravity. Yeah, 9.8 something. Yeah, just. Now, if you don't have any data and you tell a neural network to do it, it will spill bullshit. So we just so we have to tell it what the actual formula is. So the way to do it is you bring everything onto the left-hand side. This is my right. Yeah, your left. Okay. I'll bring everything to the left-hand side so that the right-hand side is 0. And you have the, we're in here, you have the mass there. Then the acceleration is the gravity and the prediction of the neural network. And it's supposed to be 0, but if say this one makes 8 and the force that it gives out is 10, then you know the difference is 2. And just plug it in the normal mean square error for the nerd. Mean square error, and you got a physics loss. And just train it like usual using the physics loss. The example is quite minimal, and I'll say it's quite misleading as well, because if you have the formula, why would you need a machine learning to do it? And so let's go back to my, I think, next slide. I should have, yeah. So this is the formula I used for my microplastic in the air. For a node out there, this is, yes, Navier-Stokes 3D version. And it's quite complex, and sometimes it does not have enough, it doesn't have answer, and it's run very, very slow. So just turn this one into a loss function, which I won't show you because it's like 300 lines of code. Yeah, meet me if you want the code. And it's on my GitHub anyway. So yeah, it's really great and really novel as well, which we are all attracted to shiny stuff. But there's a lot of, what? Is it shiny? Anyone want it? Yeah, so precaution first, when to not use it is when the problem is simple enough, when the pen drop. Yeah, simple, do not use it, just use math. Yeah, and if the physics is fast, say not at this level, so please use physics. It's simple, and the physics is known. Like you can't ask it to model the universe without giving it your knowledge first. So in physics-informed physics, and only use it when it ticks all of these three. The physics is known, I've said before, and physics is low as the image, and you don't have enough data. If you have a large amount of data and it's good enough, try to use data instead of this, because it may take like a few weeks or so to model just the physics, and training takes much longer than it's supposed to. So that's the end of my talk. Thank you. Please don't do my LinkedIn. I haven't updated.
Is that your LinkedIn QR code?
Yeah. Wow. I won't recall you, I swear. Do it. Take a picture.
I have your LinkedIn. No, we're not LinkedIn friends. Man. We're not?
I want to recall you. Oh, no.
Okay, I have two questions for you.
Yeah.
Oh, well, there's two questions for you. Oh, there's three. Oh, they're growing. They're coming in. Would it be possible, Alan, to match the German supercomputer with PINN, with PIN? How long, how much processing would that require?
To match the actual output of the supercomputer, you need the exact same supercomputer to match it. Because when talking about raw power, you need this exact configuration to get the same thing. The pins work here because we already have the data from here. But there's only 24 images. When you, if you already do CNN task, you need around 2,000 or more. But it's only 24, so we need more. We need physics help in here. So yeah, you technically can not, but it's some operation.
Continue with PIN. Is PIN a good? Does PIN a good alternative when simulating? This moves. Is PIN a good alternative when simulating something that is too expensive or is too time consuming? Is PIN a good alternative against?
Alternative what?
Alternative?
Alternative against the
against
expensive,
yeah, I guess,
computation. Yeah. It depends, like all kind of thing. But if you already have the output of some system already, and you train against it, I mean, just like for this example, right? You have the output of this one, but only a limited amount of output from that because it's very expensive. you can simulate a fraction of its power using the pin when you put the data from here to here with physics around it. Anything else?
How does the accuracy of the neural network output compare to the math-based model?
This depends on how you implement and what data you have access to when you train the pin as well. And it depends on what kind of math you're talking about, because I'll say math is nearly always 100% correct with some edge cases, and pin is just kind of simulating the math within simulation itself. So.
Is there a good way to determine the AI model speed compared to regular computation for a problem, like the simulation versus AI sim comparison?
The what?
Is there a good way to, well, this is what I have to deal with. Yeah. Is there a good way to determine the AI model speed compared to regular computation for a problem?
If you know physics, there's a set of problem called the PDE and ODE. If it falls into that kind of bucket, it's most likely going to be more expensive to run physics than actual computation. But I can't find any other application for pins in other field, unless because most of the time it's much faster to run path than machine learning, more reliable as well.
Questions keep coming. The thing is that the questions move when I'm reading them, so like here. Would PIN be ideal for a particle generator system for graphical sim systems?
What? Why would PIN be ideal for particle generator? Yeah, what is the particle generation?
I guess.
Yeah, that's my question. Sorry.
Yeah, like can you explain?
Yeah, sorry. So consider like a visual simulation system per se. The immediate relevance or the application would be, say, for like VFX or something like that, where you have a particle system generating, say,
Math is faster.
Math is faster, yes. But the problem this might solve is the physical constraints that you provide to the systems to say how a particle should behave.
I'll say much faster for a math, but like 100 operation than 1,000 operation for a machine learning model. Is that what you're talking about, or?
Kinda, yes. Yeah. So as the complexity grows, would this? I'm trying to figure out what the result from this.
My thinking is that if your particle, like for each particle, say you do one flop or something like that, this one take like 1,000 flop, 1,000,000 flop, just to like run one particle. So I say if
okay.
Yeah. So if you can run, is like don't use pin, don't use machine learning.
It's more about if it should run.
It can run, but you shouldn't run it.
Yeah.
Would you think that your method could be used not against LLM training, but against LLM prompts to achieve the same accuracy?
This one is physics. Like, what do you do with words? Like, how hype it is for words? Mm-hmm. Yeah. So, if there's a physical formula governing the whole system, use it. But for text, there are not any formula for it.
So, I have two more here.
You have two more? Sorry.
Maybe I do.
Sorry.
Can you write a physics game engine with PIN?
If you can do physics, just fine. Don't use PIN. Don't touch it. It's my trash. Yeah.
Meet me for the full formula. Is that your pickup line?
I refuse to answer.
That's a yes. Gentlemen, thank you.